Hello, I'm Dr. Jacob Hudis. If you need math or physics tutoring, please go to my website acephysics.org and book a lesson.
One of the main tools I use for nanofabrication is the electron microscope. I use it for electron beam lithography and also to image samples. And one really cool thing about being a graduate student is we get to have a lot of access to these very nice equipment that we can use for scientific research, which is also used a lot in industry. And so right now I'm going to be practicing alignment with the electron beam microscope. And so alignment is when you write patterns. This is about drawing very tiny patterns. And so when you write patterns, you have to change the magnification and also the current. And when you do that, the beam shifts. And so you need to align the beam each time you change one of these parameters. And so that's something that I'm going to be practicing today. And that's what we're doing. Alright, so you can see the chamber is vented. This is the sample stage. If you want to look inside. This is the inside of the microscope. This is the sample stage where I'm going to put my sample, and the detectors are inside there. So now that looks like my sample. Okay, so this is the piece of silicon, and put a scratch in the upper left corner, which is not that. Put a scratch to orientate myself, and so you can see there's no scratch there. So I want to try to find the scratch I put on the sample, which will help me orient it. So that's the sample. So that's the upper left corner. So that's good. So now that we're on the sample, the first thing I want to do is focus, because this is out of focus. Okay, so I'm going to start by trying to focus on the scratch. So this is a scratch that I made on the sample. I'm going to zoom in on it, and now we'll try to we're going to focus it to try to be able to get as good of a picture as we can. Looks like the scratch looks a little weird there, actually. In fact, looks like it's pointing down that direction. So I made my scratch going downward, so I was actually at the wrong corner before. Yeah, so this scratch, you can see the scratch is going that way. Very tiny scratch. And a little bit better focus. Now we'll do link to Z. And then I'm going to move this 10. Okay, see if we can do better. Alright, so now if you notice, this is 1,000 times magnified, so this is 1,000 times as big as you would see it. And a little bit tedious. This is being imaged by high voltage electrons. You can see that this is 30 kilovolts, and it's a spot size of 2.5, which is related to the current. So let's try to maybe even just get a nice edge on the screen. It's a good start, I think. I mean, we need to make a much better focus than that, but that's the way to start. If you take a picture and averages it, you can get a clearer picture of the surface. Oh, and actually there's the cross. So there are several patterns drawn on here, and this is one that we're going to use to find an orientation. I'll look at it in a second, but actually we can use the cross to focus now that I see the cross. So right now we are at magnification of 1,440. I'm going the wrong direction. Okay, magnification of 8,000, so that's 8,000 times what you would see if you were just looking at it. And now I'm going to try to focus. The reason I have this is to get so if you get this clear, then you know you got a good focus. And there's supposed to be a little triangle that I put there. We're just trying to make it so we get a nice clear image. It's really important to get a good focus when you're doing the electron microscope. And so if you want to draw a pattern, focusing is really one of the most important things. And this is okay, but we'd like to get it better. But because I'm just practicing, that's not something that has to be done right now. Okay, so now that we have a good focus on the sample, what I'm going to be using is the electron beam lithography. And so I was trying to explain that before, but that's where you actually draw these patterns, and you actually draw very tiny patterns that you create onto the surface. This was one of them, and so if you look at the little silicon substrate, you didn't see any patterns on there, and that's because they're so small. You can actually draw the entire alphabet on the tip of a pen using this machine. So it's pretty cool. So this here is the this computer is for the e-beam lithography, and actually I'm really one of the only people who knows how to use it at the whole school at this point, because it's only used in the physics department. There's only a few people who are using. A lot of people use the microscope, but very few people actually use the patterning. And that's something that I'm practicing here. Today I'm going to be doing reactive ion etching. This is argon. The argon is used just to vent the chamber, and then we have oxygen. You can etch with oxygen. Today I'm going to etch with CCl2F2. That is difluoral methane. This is our reactive ion etching system. It's old, but it works very well, and it's what we have right now. So you got to use what we have. This is the chamber where we're going to put the sample. Here's the pressure in the chamber. You can see it's 4.4 times 10 to the negative 8 torr. This is the speed of the turbo pump, which is at 27,000 revolutions per minute. Okay, so that's the speed of the turbo pump right now. So back here, this is the turbo pump, it's a turbomolecular pump. It's a very high vacuum pump, and then down here we have the roughing pump. It's just the mechanical pump. So the first thing that I want to do is I'm going to hit this button, which is gas 1. So when I hit this button, what it does is it sends a signal to slow the turbo pump down from 27,000.
AcePhysics.org. Math and Physics Tutoring with Dr. Hutis.
Revolutions per minute to 12,000 revolutions per minute, so it's going at a low speed mode, because we wanted it a low speed mode when we're doing the etching, because when we're doing the etching we're going to be letting gas in the chamber and the pressure is going to be higher, and so we want the pump to be running at a lower speed mode when the pressure's higher. I need to set the machine to the right parameters in order to make the plasma. So what's happening inside here, there's an RF coil, and we're going to let in the gas. In this case it's the CCl2F2. The gas is going to come in, and the RF coil is going to cause a plasma in here. But the plasma will only be correct when we have the right impedance values, because the impedance of the plasma changes for when you're doing different processes. And so there's an impedance matching where you can change there's a capacitor, and you can adjust the capacitor, and this tells you the forward power and the reflected power, and we want to get stable plasma. And then once I get a stable plasma, I will leave all of the controls where they are. I'll vent the system, I'll put in my sample, and then close it, leave it to vacuum, and then it'll be ready once the vacuum gets down to do the etching. Okay, so right now, gas 1 is open, so the pump is at speed. So right now the turbo pump is at 12,000 RPM. So now I'm going to open the etching gas, and so that's open, and you can see that the pressure is going way up right here. That's actually way too high, because the person before me was running a different process. So I want to try to get the pressure to somewhere around 20 millitorr, and then we're going to play around and see if we can get a good plasma. Okay, so I adjust the pressure. This is a needle valve, and this needle valve is adjusting the pressure of the gas coming in, and this is a reasonable value. And so now we're going to play around with these buttons, which are related to the impedance matching, and then we're going to see if we can get a plasma. So I'm just going to set some time just so we can actually do anything. Alright, and so now what I'm going to do is I'm going to hit RF. That's going to send an RF signal to the coil in here, and we're going to look inside and see if we have plasma, and you can see if you have a stable plasma based on the values here, and if you can see a blue glow from inside. So, hold on 1 second here. Oh, I'm sorry. Set. Okay. We have a number set, and I'm going to hit RF. So RF is on, and you can see there's a glow, but these values are terrible. So I'm going to try to adjust this here. Oh, the gas is also very oh, look at that. So you can see there we got a nice plasma at that pressure. We're going to try to well, that's a very steady plasma. You can see a nice glow in there, and these numbers are staying very constant. So now I have to load the sample, and then we'll be done. I'll let you tomorrow. Okay, so in order to load the sample, I need to vent the chamber. And in order to vent the chamber, what we have to do is we have to wait for the turbo pump to go back to speed. So now the turbo pump is going to go back to speed, and then I'm going to seal off the chamber. Once the turbo pump is up to speed, I'm going to seal off the chamber, and then vent the chamber with argon gas, and then put my sample in there and pump down again. So that's what we're going to do, and I'll show you how we do that once the pump gets back up to speed. The first thing that I have to do is isolate the chamber from all the pumps. So right now the turbo pump is pumping on the chamber, and then the rough pump is attached to the turbo pump, and the rough pump is pumping the exhaust from the turbo pump out. So the first thing that I'm going to do is I'm going to close this valve, E3, and so this is a mechanical valve that isolates the chamber from the turbo pump. Okay, so now the whole system, so now the chamber is isolated. So there's no pumps attached to the system. The rough pump is still pumping the exhaust from the turbo pump, but the turbo pump's not pumping on anything. Okay, and so I have that done. And so now what I'm going to do is I am going to vent the system. So I hit this button, I hit vent, and you can see the pressure goes up. And so what we're doing is we're filling the chamber with argon. It's a noble gas, and it's a good gas to vent with. So right now we're venting the chamber, and then I'm going to put my sample in there and pump down, and tomorrow I'll come back and etch the sample. So this is a sample right here that I'm going to etch, and you'll see me put this in the reactive ion etcher, and we're going to etch away the niobium, and this is a microwave cavity for a squid, a nano squid experiment. This coil right here is where the RF goes, and I'm going to put my sample right here. So I want to put my sample right in the center. All right, and now it's ready to etch. Okay, so now I need to pump down the system. So in order to pump down the system, we first need to do rough pumping, because you don't want to just open up the turbo pump right now when you're in this when you have a high pressure. So we're going to first rough the system down to about 50 millitorr or below, and then we can open up the turbo pump. So in order to rough the system, I have to close valve E2. And this is very important, because if I had that open, when I open this, you would suck oil into the system, and that would be very bad. So right now I'm opening the valve, which is roughing down the chamber, and we're going to wait for this to get to 50 millitorr, and you can see that the pressure is dropping. All right.
So this year we have two very deserving recipients. So the first recipient is Jacob Hudis. So Jacob is doing his dissertation research under the co-direction of Irinel Cerescu and myself. He's receiving this award for his excellent work on macroscopic quantum phenomenon in small superconducting loops.